Right now, as you watch this, the ground under you feels still. Nothing in your body says you are spinning on a planet. You are orbiting a star, racing through a galaxy. Yet every atom of you is in motion. That calm is a trick of distance and scale. In this video, we will peel back that illusion. We will follow the hidden paths of Earth, the Sun, and the universe itself to find where all of this motion is going. If you want to keep traveling through this moving universe with us, remember to like the video and subscribe. For most of human history, the sky looked like the exact opposite of motion. Night after night, the same constellations rose and set in the same places. The band of the Milky Way arched overhead like paint on a dome. The moon repeated its phases with steady patience. Planets wandered a little, but even their strange loops came back to the same patterns. To an eye with no telescope and no physics, the universe looked finished, balanced, complete. So people did the reasonable thing. They believed what they saw. If the heavens revolved in beautiful order and the ground did not shake beneath their feet, then Earth felt like the natural center of everything. Many cultures imagined some version of this story. A stable world below, a layered heaven above, and humanity standing at the pivot point. In that picture, movement belonged to the sky, not to us. We watched the dance. We did not join it. This was not just myth. It was a working model of reality. The rising and setting of the sun kept time. The slow drift of seasons matched the changing height of the sun in the sky. Eclipses could be predicted. Calendars could be built. Farmers planted, sailors navigated, priests scheduled festivals, all based on a universe that appeared to spin around a fixed Earth. When your survival depends on the sky being predictable, a still universe feels like a gift. There was comfort in that cosmic stillness. If the heavens turn around you, then you must matter in some deep way. You are not falling through space on a rock. You are standing at the center of a grand design. The universe becomes a stage, and Earth is the place where the real story happens. That feeling is powerful. It is hard to let go of, even today. Yet there was always a quiet tension hiding under the surface. The planets did not glide along perfect paths. Sometimes they slowed. Sometimes they seemed to move backward against the stars. The moon did not rise at exactly the same point on the horizon every night. Little details in the sky kept whispering that the picture might be more complicated than it looked. The stillness was already cracked. People just did not know it yet. From our modern vantage point, we know how deep those cracks go. We now understand that Earth spins once every day and orbits the Sun once every year. Our star orbits the center of the Milky Way. The Milky Way itself is moving through a larger web of galaxies. Even the fabric of space is stretching so that distant galaxies drift away from us over time. The universe is not a painting, it is a flow. So why do we not feel any of this? Why does everything still feel solid and calm? Part of the answer is speed compared to scale. You can move extremely fast and still feel nothing if everything around you moves the same way. When you sit in a smooth airplane, you can forget you are crossing a continent. Drink your coffee, watch a movie, feel almost motionless even though you are tearing through the sky. The same thing happens on Earth. The chair you are sitting on, the air in the room, the oceans, the crust beneath your feet, all share the same spin and orbit. You are inside the motion, not outside it, so you do not notice. For an observer floating in deep space, Earth would be a spinning ball rushing around the sun. For you, it is just home. Your frame of reference edits the drama away. At a deeper level, nature does not offer a universal stage that counts as truly still. Motion is always measured relative to something else. That is why different observers can tell different stories about what is moving and what is not, and all be correct within their own frame. On a train, you feel at rest while the landscape slides by. On the platform, the train is clearly the thing in motion. In space, we are always the person on the train. Once you accept that, the old picture of a fixed universe starts to dissolve. There is no cosmic throne where stillness lives. There are only layers of motion nested inside larger layers. Earth inside the solar system inside the galaxy inside a swarm of galaxies. Each step outward reveals a new current carrying us along. So the real question is no longer whether we are moving. That mystery is solved. We are. The deeper question is directional. If everything from our planet to our supercluster is caught in motion, then what path are we following? Where is the sun going inside the Milky Way? Where is the galaxy going inside the cosmic web? And in the very long run, where is the entire universe heading? To answer that, we have to strip away one layer at a time. First, the illusion of an Earth at rest. Then, the illusion of a sun at rest. Then, the illusion of a Milky Way at rest. Step by step, the stable points vanish, and a larger pattern emerges. In the next part, we will go back to the first big break in the story, when a quiet priest decided to move the sun to the center and accidentally set our entire world in motion. To see how radical our moving universe really is, we have to visit a time when the cosmos felt beautifully simple. Picture an ancient sky watcher standing under a dark dome of stars. Night after night, the pattern overhead turns like the inside of a giant sphere. The ground stays firm. The heavens spin. If you were that observer, the conclusion would feel obvious. The universe is a set of shells turning around you. Centuries later, a scholar in Alexandria turned that feeling into a detailed system. His name was Claudius Ptolemy. He took observations from Babylon, Egypt, and Greece and did something ambitious. He built a complete mechanical universe on paper. Earth sat at the center, perfectly still. Around it, in nested layers, moved the Moon, Mercury, Venus, the Sun, Mars, Jupiter, Saturn, and finally the faraway sphere of fixed stars. Beyond that, silence. In this picture, each celestial body was carried on a transparent sphere that spun smoothly. The outer shell, covered in stars, completed one turn each day and gave us night and day. It was elegant and deeply appealing. Circles were considered the most perfect shape, so the heavens, which were thought to be divine, had to move in circles. Anything less felt unworthy of a perfect sky. There was only one problem. The planets refused to cooperate. Track Mars carefully over months, and it performs a strange loop. It moves forward against the background stars, slows, seems to move backward, then resumes its path. Jupiter and Saturn do something similar, just more slowly. In a simple system of circles around Earth, that kind of backwards motion is a nightmare. Ptolemy refused to give up on circles. Instead, he made the model more intricate. He imagined that each planet was not just moving on a big circle around Earth, but also riding on a smaller circle at the same time. The small circle was called an epicycle. Its center moved along a larger circle, the deferent. As the planet looped on its epicycle, while the deferent carried it around Earth, the path on the sky twisted into loops that could mimic that backward motion. The system worked surprisingly well. With the right sizes and speeds for each circle, Ptolemy could predict planetary positions with good accuracy. When the numbers did not quite match, he added another adjustment. He introduced an off-center point called the equant. From that special point, the planet seemed to move uniformly along its path, even though the motion looked uneven from Earth. By the time he was done, the heavens had become a clock of almost absurd complexity. Yet for more than 1,000 years, this structure ruled astronomy. It guided calendar makers and astrologers. It fit within philosophical and religious ideas of a perfect, ordered cosmos. And it preserved the comforting belief that Earth was the fixed center of everything. Then one quiet man began to move the center. In the 1500s, a Polish canon named Nicolaus Copernicus spent his nights thinking about the same old problems. Retrograde motion, messy epicycles, a universe that needed patch after patch. He asked a dangerous question. What if Earth was not at the center at all? In his great work on the revolutions of the heavenly spheres, he proposed a shocking alternative. Put the sun near the center. Let Earth become just another planet. Make Earth spin once each day so that the stars appear to rise and set. Let Earth circle the sun once each year so that the sun seems to drift along the zodiac and the seasons change. Suddenly, retrograde motion becomes a perspective trick. When Earth overtakes Mars in its orbit, Mars seems to drift backward against the starry background, just as a slower car on a highway seems to slide backward when you pass it. This new picture did not instantly outperform Ptolemy in raw accuracy. Copernicus still clung to perfect circles, so his predictions were not dramatically better. The revolution was not in the numbers at first. It was in the story. For the first time, Earth was demoted from its throne. Our world was in motion, both spinning and orbiting. The heavens were not going around us. We were participating in the dance. Evidence soon followed that made this more than a clever reframe. When Galileo Galilei heard about a new Dutch invention, a tube of lenses that made distant objects appear closer, he built his own and turned it toward the sky. What he saw did not match the old crystal spheres at all. The moon was no flawless orb. It had mountains, craters, shadows. Jupiter had 4 small moons circling it, a miniature solar system that proved not everything revolved around Earth. Then came Venus. Through Galileo's telescope, Venus changed shape over time, showing a full set of phases, from thin crescent to nearly full. In an Earth-centered universe, Venus could not show all of those phases. The only way to explain what he saw was if Venus orbited the Sun, and we orbited the Sun too. The telescope had turned a philosophical idea into something almost undeniable. There was still one major flaw in the new model. Both Ptolemy and Copernicus assumed that planets moved in perfect circles. Nature disagreed. The job of fixing that fell to Johannes Kepler, working with the precise naked-eye data left by Tycho Brahe. For years, Kepler tried to force Mars into circular paths, and kept failing by tiny but stubborn amounts. Eventually, he let go of the circle. He discovered that planets move in ellipses, stretched-out circles, with the Sun at one focus. Planets speed up as they come closer to the Sun and slow down as they move away. He found a simple relationship between how long a planet takes to orbit and its distance from the Sun. In one stroke, the heavens lost their philosophical perfection and gained mathematical honesty. The orbits were not ideal shapes. They were real paths, carved out by some deeper law. By the time this new picture settled in, the universe looked very different. Earth was no longer a pedestal at the center. It was a traveler on a path around the Sun. The stars were no longer tiny points glued to a shell. They became distant suns in their own right. Motion was no longer reserved for the heavens. We were fully part of it. Yet, even in this new, sun-centered system, there was still a hidden assumption. The sun itself was treated as a kind of anchor, the quiet heart around which everything else circled. In the next part, we will see how gravity finally unified falling apples and orbiting planets, and how that same invisible pull forced us to admit that even our sun is drifting through space. Once the sun took the central seat in our mental model of the solar system, a new question appeared in the background like a shadow. Why do planets move the way they do at all? In the Copernican and Kepler world, the sun simply sat there while the planets traced their ellipses. But what was steering them? What kept Earth from flying away into the dark or spiraling into the sun? The sky had become a machine without a motor. The story of that missing motor usually starts with a falling apple. Whether the apple really hit Isaac Newton on the head is less important than the idea he saw in it. An apple falls toward Earth. The moon does not. Yet both are near our planet. What if that difference is not because one feels a force and the other does not? What if both are falling, just in different ways? Newton's leap was to imagine gravity as a universal pull. Every object with mass attracts every other object. The Earth pulls on the apple. The apple pulls back on the Earth. The same rule applies between Earth and the moon, between the sun and the planets, even between distant stars. The strength of that pull depends on two things: their masses and the distance between them. Bigger masses pull harder. Greater separation weakens the grip. This simple idea stitched the universe together. The same invisible force that made apples fall could reach all the way to the moon and keep it in orbit. Instead of rockets or crystal spheres, orbital motion became a kind of perpetual fall. The moon is constantly falling toward Earth, but always missing, because its sideways speed bends its path into a circle. Switch the moon for Earth, and Earth for the sun, and the same logic holds. With that, the strange behavior Kepler had described found a deeper cause. Planets closer to the sun feel a stronger gravitational pull, so they must move faster to stay in orbit. Planets farther out move more slowly because the sun's pull on them is weaker. This is why Mercury whips around the sun swiftly, while Neptune creeps along the edge of the planetary system. It is not arbitrary. It is gravity doing geometry in motion. You can even put rough numbers on it. Earth orbits the sun at about 30 kilometers per second, which adds up to over 100,000 kilometers per hour. Mercury, closer in, moves at roughly 1.5 times that speed. Mars, farther out, lags behind. These speeds are not chosen by some cosmic engineer. They are the only speeds that balance the inward pull of gravity with the tendency of an object in motion to keep going in a straight line. For the first time, there was one set of rules for both the sky and the ground. The fall of a stone, the swing of a pendulum, the curve of a cannonball's path, the orbit of the moon. All of them could be described with the same equations. The heavens lost their special status. They were no longer governed by higher, mysterious laws. They were part of the same physics that ruled your everyday life. This was more than a clever theory. It made testable predictions. It explained why tides rise and fall as the moon and sun tug on Earth's oceans. It allowed astronomers to calculate how the planets perturb one another's orbits. It let people predict when comets would return. The universe became a clockwork, not because everything was rigid, but because the rules were consistent everywhere. There was a quiet emotional shock in this unity. In older views, The heavens were pure, pristine, untouched by the messy forces of Earth. In Newton's universe, there was no such separation. You, the trees outside, the moon overhead, the sun itself, all of them are part of one gravitational web. We are not underneath the laws of the cosmos. We are inside them. Yet hidden inside these neat calculations was another shift in perspective that took longer to sink in. If gravity is truly universal, then there is nothing special about the sun as a reference point. The sun pulls on the planets, but the planets also pull on the sun. Every orbiting body tugs back. The entire solar system moves around a shared center of mass, a point that is sometimes inside the sun and sometimes just outside it, depending on how the giant planets are arranged. That means even in the tidy picture of the solar system, nothing is perfectly still. The sun wobbles as Jupiter and Saturn tug on it. The whole solar system moves as it orbits something even larger. Gravity does not allow true anchors. It only allows relationships. Each mass curves the path of every other mass. Everything responds. When you follow that idea far enough, a new question appears. If Earth orbits the sun because of gravity, then what does the sun orbit? If apples, moons, and planets all fall toward something, then what is the sun falling toward? The answer is not immediately obvious when you look up at the night sky with your eyes. It took centuries of better telescopes, careful counting, and patient mapping to reveal the larger structure around us. Newton had unified the motions of Earth and the motions of planets. The next step was to unify our solar system with something even bigger, to realize that the sun is just one star in a vast spinning disk. In the next part, we will climb out of the solar system entirely. We will watch astronomers turn star counts into a rough map of the Milky Way and discover that our sun is racing along a giant orbit we never feel. If gravity ties the solar system together, the next obvious question is simple and unsettling. Tied to what? Our eyes see a sky of scattered stars sprinkled in every direction. It is tempting to think of them as a random background. For a long time, that is how people thought about them. Then, one man started counting. William Herschel was a musician by trade, a telescope builder by obsession, and a mapmaker of the night. In the late 1700s, he decided to take the sky seriously as data, not just as a backdrop for myths, but as a structure that could be measured. He and his sister Caroline pointed their homemade telescopes at narrow strips of sky and counted every star they could see in each direction. It was patient, painstaking work. In some directions, the star counts were low. In others, they were astonishingly high. Over time, a pattern emerged. The richest fields of stars lined up with that faint, hazy band that stretches across the sky on dark nights. The strip of light we call the Milky Way. When Herschel turned his counts into a rough diagram, the result was striking. The stars were not spread out evenly in all directions. They formed a flattened shape, like a disk or a grinding wheel. The sun was not sitting off to one side. It seemed to be near the center of this star disk. Herschel called this structure the galactic system. To him, this was the universe itself, a star-filled pancake with us near the middle. From our modern perspective, we know he underestimated the size and misread the center. Interstellar dust blocked much of the light from faraway stars, tricking him into thinking the edge was closer than it really was. Yet for his time, this was revolutionary. He had turned the Milky Way from a painted band into an object with shape. He had placed the sun inside a stellar system instead of above it. Once you realize you live inside a structure, new questions appear. Where exactly are we in that structure? How is it moving? And how can you measure that motion when your only vantage point is a tiny planet inside the system? Imagine trying to sketch the shape of a forest while standing under one tree. That is the problem astronomers faced. The key turned out to be motion on the sky and a lot of patience. In the late 1800s and early 1900s, a Dutch astronomer named Jacobus Kapteyn took up that challenge. He was not content to know where stars appeared at one moment. He wanted to know how their positions changed over time. That meant tracking tiny drifts, sometimes just fractions of an arc-second in a year. Those small shifts are called proper motion. If you measure them for enough stars across the sky and combine that with estimates of their distances and brightness, you can start to see patterns. Kapteyn gathered observations from observatories around the world, from the southern hemisphere and the northern hemisphere, from busy star fields and quiet regions. Then he let the data speak. The stars were not drifting in random directions. They seemed to form two broad streams on the sky, moving in roughly opposite directions. At first glance, this looked like evidence for two giant swarms of stars, rotating past each other. Two star rivers sliding by. That idea was tempting, but something about it felt off. Kapteyn returned to the problem with a different mindset. Here is where the train thought experiment returns in a deeper form. When you sit in a moving train and look at people on a platform, everyone seems to drift backward. Look at another train next to you and things get confusing. It can feel like you are still and they are moving, or that you are both moving. Without the ground as a reference, motion becomes ambiguous. Kapteyn realized the same trap applied to the stars. Just because they appeared to stream in two directions did not mean they were truly doing that. It might be a side effect of our own motion through the star field. When he recalculated the data under that assumption, the pattern made much more sense. The Sun, along with its family of planets, is not resting in the middle of the star system. It is moving through it. According to Kapteyn, the Sun is heading roughly toward a point in the constellation Hercules at about 20 kilometers per second. This direction became known as the solar apex. In the opposite direction lies the point from which we seem to be coming. With that, the Sun lost its last claim to stillness. We now had a picture of our star as a traveler inside Herschel's disk, sliding through the galactic system like a ship across a crowded sea. Every star you see at night is part of that motion. Some ahead, some behind, some off to the sides, all of them orbiting something deeper that none of them can see directly. Kapteyn went further. He tried to turn his star counts and brightness measurements into a full map of the system. He assumed stars were spread more or less evenly, and that dimmer stars were usually farther away. From that, he built what he believed was the true shape of our stellar city. A flattened disk about 40,000 light-years across, with the Sun near the center. Again, dust fooled him. The dark clouds that thread through the Milky Way absorb and scatter light, especially along the plane of the disk. That made distant stars appear dimmer and closer than they truly were. So Kapteyn's universe was too small and too centered on us. Yet the basic insight was right. We live in a disk of stars. That disk rotates. The Sun is in motion within it. These early maps and motions did something profound. They shifted our sense of home yet again. We were no longer just a planet going around a star. We were passengers on a star that itself was cruising along a vast galactic orbit. Our frame of reference expanded. The idea of a fixed background faded even more. Still, big mysteries remained. What is the full shape of this disk? How far are we really from the center? What exactly are we orbiting? To answer those questions, astronomers needed sharper views, new kinds of light, and the willingness to accept that even Herschel's and Kapteyn's universes were incomplete sketches. In the next part, we will see how radio waves and giant telescope networks finally revealed the spiral structure of the Milky Way and exposed the dark heavyweight that sits at its heart. Fatalities by the early 1900s, one thing was clear. We lived inside a disk of stars, and the sun was drifting through it. What was not clear was the true size of that disk, or what exactly sat at its center. Herschel and Kapteyn had drawn bold maps, but dust and limited data had tricked them into a smaller, more sun-centered galaxy than reality. To fix that, astronomers needed two things: better distance markers and new kinds of light that could cut through the fog between the stars. The first big clue came from outside our own system. Those faint fuzzy patches in the sky that people called nebulae turned out not to be small clouds of gas inside the Milky Way. They were entire galaxies in their own right. In the 1920s, Edwin Hubble used a powerful telescope to study a nearby spiral called Andromeda. Inside it, he found a special kind of star, a Cepheid variable, which pulses in brightness in a predictable way. Thanks to earlier work by Henrietta Leavitt, astronomers knew that the period of that pulsing reveals the true brightness of a Cepheid star. Compare that true brightness with how dim it appears, and you can estimate its distance. When Hubble did the math for Andromeda, the answer was shocking. It lay far beyond the edge of the Milky Way. Our galaxy was not the entire universe. It was one island in a vast cosmic sea. That realization helped in a subtle way. By comparing the shapes and motions of other galaxies that we could see from the outside, astronomers began to infer what our own might look like from a distance. Many spirals showed a bright central bulge, a flat disk, and winding arms. It was natural to suspect that the Milky Way shared the same basic structure. The problem was seeing through our own dust to confirm it. Visible light struggles in the crowded plane of the galaxy. Dust grains block and scatter it, turning the heart of the Milky Way into a dark lane on the sky. So astronomers switched to radio waves. Neutral hydrogen atoms emit a very specific radio signal with a wavelength of 21 centimeters. That longer wavelength passes through dust with ease. By tuning radio dishes to that line and scanning the sky, researchers could trace the distribution of hydrogen gas along the spiral arms. As those hydrogen clouds move around the galaxy, their radio signals are slightly shifted in frequency. That shift reveals how fast they are moving toward or away from us. Combine those speed measurements with their positions on the sky, and you can start to reconstruct the rotation of the Milky Way from the inside. The picture that emerged was a large spiral disk, tens of thousands of light-years across, with our sun sitting roughly 2/3 of the way out from the center. A Dutch astronomer named Jan Oort took this further. He studied the motions of stars in our neighborhood and realized the galaxy does not spin like a solid wheel. Stars closer to the center orbit faster. Those farther out orbit more slowly. The pattern is more like a whirlpool than a rigid disk. From this differential rotation, Oort estimated that the Sun is about 30,000 light-years from the galactic center and streaking along its orbit at more than 200 kilometers per second. At that speed, it takes roughly 225 million years to complete one lap, one galactic year. Every star you see in the night sky is riding along a similar path. Some nearer the center, some farther out. All of them are part of this grand rotation around whatever lies at the middle. That raised an obvious and unsettling question. What are we orbiting? What kind of mass could hold together hundreds of billions of stars moving that fast? To answer that, astronomers needed incredible precision near the galactic core, a region heavily obscured by dust. Again, radio waves came to the rescue. In particular, they turned to the Very Long Baseline Array, a system of 10 radio antennas spread across the Western Hemisphere. When these dishes observe the same object at the same time and combine their signals, they act like a single giant telescope, about as wide as the distance between the antennas. This trick, called interferometry, gives the array astonishing resolution. It can measure changes in position on the sky so tiny they are expressed in micro-arcseconds, the equivalent of spotting a coin on the moon from Earth. Using this sharp vision, astronomers tracked compact radio beacons known as masers. These are naturally occurring microwave lasers produced in gas clouds near newborn stars. They are bright, pinpoint sources that sit deep in the Milky Way, close to the galactic center. By watching these masers over years, scientists measured their proper motion across the sky and their velocity toward or away from us. That gave a three-dimensional picture of how gas and stars move near the core. The closer they looked, the stranger the motions became. Objects close to the center were whipping around at incredible speeds, far faster than could be explained by the visible cluster of stars alone. If you calculate how much mass is needed to keep those fast-moving objects in orbit, you get a number that is hard to believe. Something in the inner few light hours of the galaxy must weigh more than 4 million suns. Yet it emits almost no visible light. It does not spread that mass out over a big volume either. It is packed into a region smaller than the orbit of Mercury. We know of only one kind of object in physics that fits those extremes: a black hole. Not a small one born from a single collapsed star, but a supermassive black hole, a monster that outweighs millions of stars and bends space-time so strongly that not even light can escape from its immediate surroundings. The radio source at the Milky Way's center, known as Sagittarius A star, marks this location. In infrared and radio images, we see stars near it racing along tight paths, executing partial orbits over just a few years. Their motions are like test particles in a gravity laboratory. Plug their speeds and distances into Newton's laws, and the answer comes back again and again. There is an unseen mass of about 4 million suns sitting in the dark. So when you think about the sun's path, it is not just drifting vaguely through a star field. It is part of a vast whirlpool of stars and gas, spiraling around a supermassive black hole. Our entire solar system traces a slow, graceful orbit around this dark anchor. One lap every couple hundred million years. We are currently somewhere on a minor branch called the Orion Spur, a small sidearm between larger galactic arms, riding a wave that gently oscillates above and below the galactic plane. This is our true cosmic neighborhood. A rotating disk of stars, threaded with spiral arms, all swirling around a quiet but immense black hole at the center. Yet even this is not the final layer of motion, because the Milky Way itself is not stationary. It is one galaxy among many, drifting through a larger landscape of groups, clusters, and superclusters. In the next part, we will step outside our galaxy and watch as whole star cities move, collide, and reshape one another. including the future encounter that will transform the Milky Way forever. By now, our picture of motion has expanded from falling apples to orbiting planets to a galaxy spinning around a black hole. It is tempting to stop there and declare victory. The Milky Way becomes our new island, a grand but fixed backdrop. Yet when we step even farther back, that sense of stillness shatters again. Whole galaxies are in motion too, drifting, colliding, and being reshaped over billions of years. To understand how we first discovered this, imagine standing on a sidewalk as a car speeds past. As it approaches, the engine sounds higher pitched. As it races away, the sound drops. This is the Doppler effect. When a source of waves moves toward you, the waves bunch up. When it moves away, they stretch out. Sound waves do it in air. Light waves do it in space. If a star or galaxy is moving toward us, the light we see from it is shifted slightly toward the blue end of the spectrum. That is called a blue shift. If it is moving away, its light is shifted toward the red. That is a red shift. By measuring exactly how much the lines in a galaxy's spectrum are shifted compared to where they should be, astronomers can calculate how fast that galaxy is coming or going along our line of sight. In the early 20th century, Edwin Hubble and others began measuring red shifts and distances for many galaxies. The pattern they found was jaw-dropping. Almost all of the galaxies were red-shifted. They were moving away from us. Even more strange, the more distant a galaxy was, the faster it seemed to recede. A nearby galaxy might be moving away at a few hundred kilometers per second. A faraway one might be racing away at thousands of kilometers per second. This relationship, now known as Hubble's law, revealed something deeper than simple motion through space. Space itself is expanding. The distance between galaxies grows over time, like points drawn on the surface of an inflating balloon. No galaxy sits at the true center. Every galaxy sees most others moving away. The universe is not static at all. It is stretching. That discovery changed everything. If space is expanding today, it must have been smaller in the past. Wind the film backward, and all galaxies come closer and closer together, hinting at a hot, dense beginning that we now call the Big Bang. Suddenly, the question of where everything is going becomes tied to how this expansion will evolve. Yet even in this grand outward flow, there are local exceptions. One of those exceptions is our nearest large neighbor, the Andromeda Galaxy. Early measurements of its spectrum showed something odd. Andromeda is blue-shifted. Its light waves are squeezed rather than stretched. Instead of riding the expansion away from us, Andromeda is coming toward us. At first, all astronomers could say was that the approach speed was significant. The full three-dimensional path was still a mystery. A century of better technology turned that mystery into a detailed prediction. Space telescopes like Hubble, combined with the precise star positions from the Gaia mission, and radio observations from arrays such as the Very Long Baseline Array, have allowed astronomers to track Andromeda's motion both toward us and sideways across the sky. That sideways drift is tiny, but over many years it can be measured. When you combine these components, a clear picture appears. The Milky Way and Andromeda are not simply passing near each other. They are bound together by gravity in a shared dance. Right now, Andromeda is about 2.5 million light-years away and is moving toward us at roughly 110 kilometers per second. Our galaxy is not standing still either. When you account for the motion of our entire local group of galaxies, the gap between us is closing at roughly 500 kilometers per second. Those speeds sound dramatic, Yet space is vast. At this rate, the first close encounter between the two galaxies is expected in about 4 to 5 billion years. On human timescales, that is forever. On cosmic timescales, it is an appointment already penciled in. So what will that encounter look like? It is easy to imagine a chaotic crash, stars hitting stars, worlds shattered. Reality is stranger and more subtle. Galaxies are mostly empty space. In our region of the Milky Way, the average distance between stars is 4 or 5 light years. That is tens of trillions of kilometers. Even in the crowded central bulge, stars are typically a light year or more apart. If you scaled a star down to the size of a ping pong ball, the next nearest star would sit hundreds of kilometers away. So when two galaxies interpenetrate, their stars almost always miss one another. Instead of a direct smash, you get a slow gravitational ballet. As Andromeda and the Milky Way draw near, their mutual gravity stretches them. Long tidal tails of stars and gas are pulled out. Spiral arms twist and warp. Some stars are flung into long arcs that extend far beyond the original disks. Others plunge toward the combined center. The first flyby is fast on a cosmic clock, perhaps a few 100 million years. After that, the galaxies swing past, slow, then fall back toward each other again. Over roughly 1 to 2 billion years, repeated passes and gravitational friction sap their orbital energy. Eventually, their cores sink together and merge. The end product is not a neat spiral, but a large, puffed-out elliptical galaxy. Astronomers even have a nickname for this future hybrid: Milkomeda. What happens to our Sun in this scenario? The most likely outcome is surprisingly gentle. Our star will almost certainly not collide with another star. Its orbit will be rearranged by the changing gravitational landscape, perhaps flung farther from the new galactic center into a more elongated path. The night sky, however, will be transformed for any hypothetical observers. Giant arcs of stars, double galactic cores, and streams of gas will fill the heavens during the height of the merger. This future collision reminds us of a key lesson. Even when the overall universe is expanding, gravity can pull local regions together and override that expansion. The Milky Way and Andromeda are falling toward one another, even as more distant galaxies continue to drift away, faster and faster. Our local story is written by gravity on the scale of a small group of galaxies. But that group is not isolated either. It is part of something larger, sliding through an even grander pattern of motion. To see where the Milky Way is going beyond its date with Andromeda, we have to zoom out again and watch how galaxy groups gather into clusters and clusters into superclusters, all flowing along invisible rivers in the cosmic web. That is where we are headed next. So far, our journey has stayed close to home in cosmic terms. We have watched the Sun circle the galactic center and seen the Milky Way preparing for its slow dance with Andromeda. Now it is time to zoom out again, because galaxies do not float alone. They cluster, they form chains, and they stream together through a much larger landscape. Our home is not just a galaxy. It is a node in a vast web. The first step up from the Milky Way is something called a galaxy group. Our own is simply named the local group. It contains roughly 80 galaxies spread across about 10 million light-years. The Milky Way and Andromeda are the two giants in this neighborhood, each surrounded by small satellites. The large and small Magellanic Clouds orbit the Milky Way. Dwarfs like M32 and M110 cling to Andromeda. Together they form a loose gravitational family. This family is bound by gravity, That means the galaxies inside it are not just drifting away with the general expansion of the universe. They orbit a shared center of mass, tugging on one another and slowly evolving as a unit. Yet the local group itself does not sit still in space. It moves through a larger environment, falling into a deeper gravitational well. To see that, you have to look beyond the immediate neighborhood to the next rung on the ladder. Groups of galaxies gather into clusters. A cluster is a much larger, richer collection of galaxies bound together. Our local group is a small member of the Virgo cluster, a collection of more than 1,000 galaxies. The Virgo cluster lies about 65 million light-years away and contains giant ellipticals and spirals, all orbiting within a shared cloud of dark matter and hot gas. The important point is that we are not just sitting next to Virgo, we are moving toward it. Measurements of galaxy motions show that the entire local group is falling toward the center of the Virgo cluster at hundreds of kilometers per second, roughly 600 kilometers per second, according to current estimates. On top of the motion toward Andromeda and the spin around the Milky Way's black hole, our whole neighborhood is sliding down a larger gravitational slope. But the Virgo cluster is not the top of the hierarchy either. Clusters themselves gather into even larger arrangements, called superclusters. These are the biggest structures we have mapped in the nearby universe, spanning hundreds of millions of light-years. For a long time, astronomers thought of superclusters as separate islands. Then, better data revealed that those islands are connected into a single, sprawling basin of flow. Our supercluster is called Laniakea, a Hawaiian word that means immense heaven. It lives up to the name. Laniakea stretches more than 500 million light-years across and contains on the order of 100,000 galaxies. It includes the Virgo cluster, the Hydra, Centaurus region, the Pavo-Indus structures, and the southern supercluster, all linked by filaments of galaxies and gas. How do we know where all of those galaxies are going? Positions on the sky alone are not enough. Redshift gives us a handle on how fast galaxies recede, with the general expansion, but that is only part of the story. Astronomers needed a way to measure which galaxies are moving faster or slower than the pure Hubble flow, and in what directions. Those deviations are called peculiar velocities, and they reveal the underlying gravitational landscape. Measuring them is tricky. You cannot simply watch a faraway galaxy crawl across the sky. Its sideways motion is far too small. Instead, you combine multiple distance measuring tricks. One of the most important is the Tully-Fisher relation, which connects how bright a spiral galaxy should be to how fast it rotates. Compare that expected brightness with what you actually see, and you can estimate its distance. Add other methods, such as surface brightness fluctuations in elliptical galaxies and the known brightness of exploding Type 1a supernovae, and you can build a catalog of distances. Once you know a galaxy's distance and its redshift, you can ask a crucial question. If the universe were expanding smoothly, how fast should this galaxy be receding? Then you compare that expectation to the actual redshift-based speed. The difference is its peculiar velocity, the motion caused by local gravity rather than global expansion. This is where the Cosmic Flows projects come in. Cosmic Flows 2 and the later, richer Cosmic Flows 3 are massive surveys that gather distances and velocities for thousands of galaxies. Using these data, researchers constructed three-dimensional maps not just of where galaxies are, but of how they are moving through space. The result looks less like a random swarm and more like a set of currents in a cosmic ocean. Galaxies do not drift aimlessly. They stream along filaments toward dense regions and away from emptier ones. When the team behind Cosmic Flows 3 mapped these flows in our part of the universe, a pattern emerged. Many galaxies, including those in our local group and the Virgo cluster, were not only participating in the general expansion, they were also sliding in a particular direction across that expansion, toward a region in the sky near the constellations Centaurus and Norma. There was a problem, though. When telescopes tried to look directly in that direction, their view was blocked. Our own Milky Way runs across that part of the sky. Thick lanes of dust, gas, and foreground stars create a blind spot known as the zone of avoidance. It is like trying to survey a distant landscape while a bright tree trunk sits directly in front of your face. You can feel something pulling, but you cannot see it clearly. Still, the motion was undeniable. Galaxy clusters leaned toward that region. Peculiar velocities pointed that way. To explain this, astronomers proposed that a massive concentration of matter lay behind the glare and dust. They called this unseen influence the Great Attractor. Not because it was a single object, but because it behaved like a gravitational sink, drawing in whole swaths of the nearby universe. As X-ray telescopes and infrared surveys improved, they began to pierce parts of the zone of avoidance. Bit by bit, a picture emerged. Behind the Milky Way's veil, astronomers found large clusters of galaxies. One of the most important is the Norma cluster, roughly 220 million light-years away. It sits near a much larger overdense region, the Shapley supercluster, one of the biggest known agglomerations of mass in our local universe. Together, these hidden giants help explain the flows mapped by Cosmic Flows. Our local group, the Virgo cluster, and much of Laniakea are sliding toward this massive region of space. We are not falling neatly into a single point. We are moving along curved paths shaped by the distribution of mass around us. The Great Attractor is less a destination and more a deep valley in the landscape of gravity. Yet this pull is not the only thing shaping our path. The same maps that revealed this attractor also hinted at something just as important on the opposite side of the sky. A region not of excess matter, but of surprising emptiness. To understand where we are truly headed, we have to explore how both overdense and underdense regions combine to guide the flow of galaxies. That is the story of a strange feature with an even stranger name, the dipole repeller, and it is where we turn next. When you hear the name Great Attractor, it is easy to picture a single monstrous object, some kind of cosmic drain pulling everything in. The reality is more subtle and more interesting. The Great Attractor is really a nickname for a region of unusually high mass, a cluster of clusters, a zone where gravity is stronger than average because there is more stuff there, both visible and dark. Our local group and much of our supercluster slide gently in its direction, like leaves drifting toward a low spot in a lake. But the universe rarely lets one influence act alone. When astronomers mapped galaxy motions using the Cosmic Flows data, they did not just see a simple inward stream toward one point. They saw something shaped more like a dipole pattern, a two-sided flow. Galaxies within hundreds of millions of light-years were not only heading toward one general region near the Shapley supercluster and the Norma cluster, they were also moving away from another region on the opposite side of the sky. This opposite region is where the story gets strange. When astronomers looked there, they did not find a hidden megacluster. They found the opposite, a cosmic desert, a large, underdense region with far less matter than average. Almost no rich clusters, very few galaxies at all. In everyday language, it is a void. Not perfectly empty, but thin enough that its gravitational pull is weaker than its surroundings. So why does that matter? Gravity pulls. It does not push. Yet when you put an overdense region on one side and an underdense region on the other, you get something that feels a lot like a push and a pull combined. The heavy side tugs harder. The empty side tugs less. The result is a net flow away from the void and toward the mass. To get an intuition, picture yourself floating in a slow-moving river. On one side of you is a deep channel where the current is strong. On the other side is a shallow eddy where the water barely moves. You are not being pushed by the still patch. You are simply more strongly carried by the faster flow. Given time, you drift toward the deep channel and away from the quiet pocket, even though nothing ever pushes you. In the cosmic version of this story, the deep channel is the great attractor and the Shapley supercluster region. The quiet pocket is this large, underdense zone. When scientists modeled the three-dimensional galaxy flows, they saw that the pattern could be explained if there were two key features shaping the currents: a massive attractor on one side and a low-density void on the other. They gave the void an evocative name: the dipole repeller. Despite the name, the repeller does not really repel. It is simply a place where there is less mass to hold galaxies back. In the same way that a ball will roll away from a low ridge toward a deeper valley, galaxies naturally drift away from underdense regions and into overdense ones. Over time, this process sharpens the contrast. Clusters grow richer, voids grow emptier. The cosmic web becomes more pronounced. For our own neighborhood, this means we are caught in a gentle tug-of-war. On one side, the Shapley supercluster and its surroundings exert a strong pull. On the other, the dipole repeller lets us slip away more easily. The result is a coherent flow. The local group, the Virgo cluster, and many neighboring structures stream in roughly the same direction, away from the void and toward the attractor. It is important to see how this changes our sense of motion. We are not falling into a single drain like water going down a sink. We are surfing a shaped space-time landscape. Peaks and valleys in the distribution of matter guide our path. Overdensities act like hills that draw us in. Underdensities act like holes in the fabric where the pull is weaker, so we drift away. The pattern is continuous and evolving, not mechanical and fixed. This tug-of-war also reveals something profound about how structure grows in the universe. Early on, small variations in density, some regions slightly heavier, some slightly lighter, were amplified over billions of years. Gravity pulled more matter into the heavy spots, making them heavier still. The light spots lost matter to their neighbors and became emptier. The great attractor and the dipole repeller are not individual objects. They are the grown-up versions of those tiny early ripples. Even with all of this complexity, one thing is clear. On scales of hundreds of millions of light-years, gravity is still in charge of where matter goes. Galaxies cluster. Flows form. Superclusters pull. Voids release. Yet there is an even larger trend layered on top of all of this. The very stage on which these flows play out is stretching. Space itself is expanding, and doing so faster and faster. The great attractor may guide our motion within a certain volume of the universe, but it does not decide the final fate of everything. To see where all of this is headed in the very long run, we have to understand what is driving that accelerating expansion. We have to confront the strangest player in this story, the one that does not clump into stars or galaxies at all, yet dominates the cosmic budget. Dark energy. That is where our journey turns next. On these huge scales, gravity feels like the main character. It gathers gas into stars, stars into galaxies, galaxies into clusters, clusters into superclusters. The great attractor pulls, the dipole repeller releases, and everything seems to follow the curves that mass carves into space-time. For most of the 20th century, cosmologists assumed that if you zoomed out far enough, gravity would eventually slow the expansion of the universe itself. Maybe it would never fully stop, but it should at least be breaking. That assumption led to a simple project in the 1990s. Two independent teams set out to measure how quickly the expansion was slowing down. They used exploding stars called Type 1a supernovae as cosmic landmarks. These are special. A white dwarf in a binary system steals matter from its companion until it reaches a critical mass. Then it detonates in a runaway fusion event. Because the trigger mass is nearly the same each time, the peak brightness is also similar. That makes these supernovae excellent distance markers. The idea was straightforward. If you know how bright one of these supernovae truly is, and you measure how bright it looks, you can estimate how far away it is. Combine that distance with the redshift of the host galaxy, and you get a snapshot of how fast the universe was expanding when the light left. By collecting many such snapshots at different distances, you can trace how the expansion rate has changed over time. Everyone expected to see a slow cosmic breaking. Instead, they found the opposite. The distant supernovae were dimmer than they should have been in a slowing universe. Their host galaxies were farther away than expected, which meant the expansion had not been gently decelerating. It had been speeding up. The universe was not just expanding, the expansion was accelerating. This result was so strange that the teams checked and rechecked their work. Other groups repeated the measurements with more supernovae and different telescopes. The pattern held. In 1998, the conclusion became unavoidable. Something unseen was driving the universe apart faster and faster. It was not ordinary matter. It was not the dark matter that holds galaxies together. It was something else. We now call that something dark energy. The name is more of a question mark than an answer. We do not know what dark energy is made of, or even if it is a substance in any normal sense. All we know is that whatever it is acts like a negative pressure built into the fabric of space, causing the expansion to accelerate instead of slow down. When cosmologists add up the cosmic energy budget, they get a surprising breakdown. Only a small slice, less than 5%, is ordinary matter, the stuff that makes up stars, planets, and you. Roughly a quarter is dark matter, and the rest, about 70%, appears to be dark energy. One simple idea is that dark energy is just the vacuum energy of space. In quantum field theory, even empty space is not truly empty. It seethes with virtual particles that pop in and out of existence for brief moments. That restless activity should give the vacuum a kind of baseline energy. Through Einstein's equations, any energy density in space affects how space-time curves and expands. So it is natural to wonder if this vacuum energy is what we are measuring as dark energy. There is a huge problem, though. When physicists calculate how big the vacuum energy should be using standard quantum theory, they get a number that is wildly too large. The prediction overshoots the observed dark energy density by a factor of about 10 raised to the power of 120. That is a 1 followed by 120 zeros. It is the most embarrassing mismatch between theory and observation in all of physics. So we are left in a strange position. We can measure the effect of dark energy very precisely. We can see how it shapes the overall expansion of the universe. Yet, we do not know what it actually is. We give it names, like cosmological constant, when we think it might simply be a fixed energy built into space-time, or dynamic field, when we imagine it evolving over time. Under those dry terms lurk radically different futures. To picture one of the most extreme, imagine that dark energy is not constant, but slowly grows stronger with time. At first, its push is gentle, almost unnoticeable compared to gravity on small scales. Galaxy clusters stay bound. Galaxies remain intact. Solar systems are fine. But as the universe ages, dark energy's influence rises. The expansion not only accelerates, the acceleration itself speeds up. In this scenario, often called the Big Rip, there comes a time when no structure can resist. First, galaxy clusters are pulled apart, as the space between their member galaxies stretches faster than gravity can keep them together. Later, individual galaxies begin to be unbound. Stars previously orbiting in graceful loops drift away into the deepening dark. Still later, star systems like our own are shredded. Planetary orbits become unstable. Planets are flung into interstellar space. The process does not stop there. As the acceleration climbs, even the bonds inside galaxies fail. The Milky Way, or whatever merged remnant exists by then, would be torn into wandering stars. Eventually, the tidal effect of expansion becomes strong enough to overcome the gravity that holds planets together. Then the forces that bind atoms, and finally, the forces that bind the particles inside protons and neutrons. In the final moments before the rip, matter itself is torn apart. Some versions of this model suggest a timeline where a universe like ours would meet this fate in something like 22 billion years. That number is not a prediction carved in stone. It comes from a particular way of describing dark energy's behavior. Change the details, and the schedule changes, or the rip may never happen at all. What matters is the logic. If dark energy grows stronger with time in just the wrong way, everything can be unmade by expansion itself. The opposite vision is called the Big Crunch. In that picture, dark energy is not a permanent feature. Perhaps it decays over time or changes sign. If it weakens enough, gravity could eventually take over again on the largest scales. The expansion would slow, halt, and then reverse. Galaxies that are currently drifting apart would begin to approach. Clusters would merge. The universe would shrink. Temperatures would climb as everything is squeezed into a smaller and smaller volume. Structures would collapse. The sky would grow brighter with the light of crowded, colliding stars. In the last stages, all matter and radiation would be compressed into a hot, dense state, maybe similar to the conditions near the Big Bang. Some theories imagine a bounce that triggers a new expansion. Others end the story there. Right now, the data favor a quieter alternative. Observations of the cosmic microwave background and distant galaxies suggest that dark energy behaves very much like a constant energy density built into space. If that continues to hold, then neither a rip nor a crunch is likely. Instead, the universe coasts toward a slower, colder ending. That ending is less dramatic than shattering everything or crushing everything, yet in many ways it is even more haunting. To see what that looks like, we have to follow the story far beyond the lives of stars and galaxies, into a future where expansion keeps going, energy thins out, and the universe slowly forgets that it was ever bright at all. That is the path of the Big Freeze, and it is where we finish our journey. In the last part, we met some of the most dramatic possible endings the universe could choose. A big rip that tears everything apart, and a big crunch that collapses everything back together. Both are cosmic thrillers. Yet the future that best matches what we see right now is quieter. No final explosion, no catastrophic implosion. Just a long, slow dimming. The big freeze. A universe that does not die in fire, but in silence. The key is how dark energy behaves. All our best measurements so far point to a simple picture. Dark energy acts very much like a constant energy density built into the fabric of space. As the universe expands, the amount of dark energy in any given chunk of space stays roughly the same. Since more space appears over time, the total amount of dark energy grows, and its influence on the expansion never fades. In this scenario, the acceleration of the universe continues, but not wildly enough to rip apart things that are already tightly bound. Gravity still wins on small and medium scales. Galaxies stay intact. Galaxy clusters remain held together. Our future merged galaxy, the product of the slow collision between the Milky Way and Andromeda, will settle into a massive elliptical island of stars. Locally, things look stable. Globally, the gap between islands grows. As time passes, distant galaxies race away from us faster and faster. Eventually, they cross a strange boundary. The expansion of space carries them away so quickly that light they emit can never reach us, no matter how long we wait. They slip beyond our cosmic horizon, not because they vanish, but because the universe stretches the space between us too fast for their light to ever catch up. Give the cosmos on the order of 100 billion years, and most of what we currently see through telescopes will be gone from view. The sky will no longer reveal a rich cosmic web. For any astronomers alive in that distant future, the universe will appear small and empty, with only their own galaxy visible. The evidence of an expanding universe and a hot, dense beginning will be much harder to read from that lonely vantage point. Inside that last visible galaxy, life goes on for a while. Star formation continues as long as there is cold gas to collapse into new suns. But that supply is not endless. Each generation of stars burns through hydrogen, fuses it into heavier elements, and returns part of that material to interstellar space through winds and supernova explosions. Over immense stretches of time, this recycling slows. The gas reservoir dwindles. Estimates suggest that after roughly 1 trillion years, star formation across the universe will effectively stop. No new stars will light up. The existing stars will be all there is. The long-lived red dwarfs, tiny and cool compared to our sun, will dominate this era. They burn their fuel very slowly and can shine for trillions of years. They will be the last true stars, glowing faintly in a sky that grows ever darker. As those final stars exhaust their fuel, they leave behind remnants. White dwarfs, the cooling cores of sun-like stars. Neutron stars, the ultra-dense remnants of massive explosions. Brown dwarfs, failed stars that never quite ignited. Black holes, the collapsed hearts of the heaviest stars and the giants at galactic centers. The bright stellar era gives way to what physicists sometimes call the degenerate era, a universe made of leftovers. In this era, galaxies still exist, but they are ghostly. Their light comes mostly from cooling embers. Over unimaginable timescales, gravitational encounters slowly reshape these systems. Stars and remnants fling one another into new orbits. Some are kicked out of galaxies entirely and wander alone in intergalactic space. Others spiral toward the center and feed the supermassive black hole, which grows heavier with each swallowed object. Black holes, for a while, seem like the ultimate winners. In a darkening universe, they remain as the deepest wells of gravity, quietly devouring anything that strays too close. Then, quantum mechanics steps back into the story. In the 1970s, Stephen Hawking showed that black holes are not perfectly black. They can slowly lose mass through a process now called Hawking radiation. The effect is tiny for stellar mass black holes and almost impossibly small for supermassive ones, but time is on its side. A black hole with the mass of our Sun would take about 10 to the power of 67 years to evaporate. Heavier ones last even longer. Yet, in a big freeze future, time is not in short supply. Given enough eons, every black hole, from the smallest to the giants at galactic centers, will radiate away its mass. Along the way, another process might unfold. Some theories predict that protons, the particles that make up the nuclei of atoms, are not truly eternal. If proton decay is real, then on timescales around 10 to the power of 36 years, all ordinary matter would gradually fall apart. Atomic nuclei would disintegrate. The solid matter we are familiar with would turn into a thin bath of lighter particles and radiation. Combine proton decay with black hole evaporation, and the far future universe starts to look very simple. No stars, no planets, no solid matter, no black holes. Just a sparse fog of low-energy photons, stray neutrinos, and perhaps a few stable particles drifting through an ever-expanding, ever-cooling space. The average temperature creeps closer and closer to absolute zero. There are no large-scale energy gradients left, no way to build engines, stars, or living things. This is what physicists mean by the heat death of the universe, a confusing name for a state that is incredibly cold. Heat death is not about temperature being high. It is about entropy being maximized. All the easy ways of turning energy into work have been used up. The universe has spread its energy out so evenly that nothing interesting can happen on its own. In this final picture, motion still exists in a technical sense. Particles still move. Space still expands. But the grand, coherent motions that shaped our path Earth around the Sun around the galaxy through Laniakea, all of those have faded into history. The universe has no large structures left to rearrange. It has reached a kind of cosmic boredom. This ending is not guaranteed. It depends on assumptions about dark energy that we are still testing. New physics could rewrite the script. Yet, even as we admit our uncertainty, one thing stands out. We live in a very special sliver of cosmic time. The universe is old enough for heavy elements, planets, and life, yet young enough that stars still shine, galaxies still form, and the sky still tells the full story of its own birth. When you look up at the night sky, you are seeing a rare phase in the life of the cosmos. A moment when motion has carved rich structure out of a simple beginning, but the final fade into uniform darkness has not yet begun. Earth spins beneath you. The sun carries you around the galaxy. The galaxy carries you through the cosmic web. Dark energy stretches the stage under all of it. Where is everything in the universe going? In the most likely story we can tell today, it is going outward into more space, toward more emptiness, toward a quiet future where motion continues, but meaning has drained away. Yet that very bleakness gives our current moment a strange kind of beauty. In a universe that will eventually forget its own complexity, we are part of the brief chapter that remembers, measures, and wonders.